Hi all, I'm Nida Shamim. I'm a research scholar from Indian Institute of Science, Bangalore. I'm in my 4th year of my PhD and admitted in Center for Nanoscience and Engineering. Many of you know me and have interacted with me in the past 5 weeks. And in the past 5 weeks, we have studied about the course of Introduction to Photonics, in which we have done a detailed study of all the optical phenomena associated with light, that there is dispersion, refraction, reflection, total internal reflection. We have studied about interferometers and its applications, and also about electromagnetic optics, that light can be treated as a wave as well as photon, and how this can be applicable in fiber optics. That is, this light is transmitted along large distances using fiber optics, where the phenomena of total internal reflection is applied. And also we have learned about how this transmission can be done without much losses using optical amplification by a 3-level or 4-level systems. So when we talk about fiber optics, we generally what do we talk about? How does a fiber optics, or the construction or the structure of fiber optics, look like? So this is my fiber optics. We have a cladding. Okay, it has some refractive index in cladding. Okay, and then in between these two cladding, we have a core material which has a refractive index of n core. So n core, that is and it should be such that the refractive index of the core is greater than the refractive index of the cladding. And this is done by, we have studied this before, because when some signal that we want to transmit from one end to another enters this at some angle, which is called the acceptance angle, at that angle, if it enters, it gets totally internally reflected. That is the reason because why it gets totally internally reflected, because n core is greater than n cladding. And I have already given the condition that it has to be incident at a certain angle such that there should be total internal reflection. Okay, so now these fiber optics is used to transmit signals from one end to another. So in this, we want the signal at the receiving end same, as strong as a signal that has been transmitted. But what happens along the distance through which it travels? There can be some some centers of absorption, that is beyond the wavelength of 1.6 micrometers. There is infrared absorption, and within the wavelength of 1 micrometers to 1.6 micrometers, there are scattering. There are some scattering centers, so there will be Rayleigh scattering. Okay, so because of this, there are losses in the medium. So the signal that we receive, if we send a very strong signal here, so signal that we receive will be a weak signal. Okay, so now what will happen? So now what do we do? How do we solve this? So for that, what are we going to do? We will amplify our signal which we are transmitting at the transmitting end. So now, sorry, not at the transmitting end, but along the whole length of the fiber. So how do we amplify this signal? In a previous thing, we have studied about some amplification. One is spontaneous emission. So in spontaneous emission, what happens is, like, light can have the same frequency as the spontaneously emitted photon may have the same frequency as that of the signal photon, but it may be out of phase. And because of that, what will happen? If it's out of phase, there can be what? Interference, disruptive, constructive. So spontaneous emission will lead to more of noise of my signal. Okay, so because of spontaneous emission, there will be noise. Okay, so now what do? We will do stimulated emission. Okay, in stimulated emission, the emitted photon and the signal photon have the same frequency, same phase, and everything is same. So that leads to amplification of my signal photon. So for the stimulated emission, what do we want? We pump this atoms in the ground state to the higher excited state, and in the higher excited state it is staying. And what is happening over here? What is happening over here? It should stay for some excited state. This is an excited state. It should stay here for quite a good amount of time. And for that, it should stay here for quite a long amount of time. And for that, what will happen? Tell me. So for that, what do we need? We need it should stay there for till the time another signal photon comes. Then it will go down. That is, signal photon comes here. It should be here. Sorry. Signal photon comes here. So the excited atoms should come down. That is why it's called stimulated emission. It gets stimulated. It comes down, emitting another photon, which is same as that of the signal photon. So there is amplification. So for that, it should have a longer lifetime for the excited state. So whatever material we are using for this stimulated emission. So that's why we are using erbium. So this whole session is on erbium doped fiber amplifier, and we'll do a basics of lasers. And here what do we see? Erbium doped fiber amplifier, that is, we have this fiber amplifier, and this erbium has a relatively longer lifetime of the excited state. So it can stay in the excited state, that is, population inversion will be maintained for a longer time till a signal photon comes. So this fiber amplifier, that is the core of the fiber, will be doped with erbium. That is erbium atoms. Sorry, it will be doped with this erbium atoms, and we'll have the signal photons, and we'll pump this erbium atoms to the excited state, and this erbium 3, and this is what we call erbium 3 plus silica, and this is what you call erbium doped fiber amplifier. So let's move on. Okay, what do we talk about? So I had told you about erbium doped fiber amplifier, and what is erbium? Erbium doped fiber amplifiers are very long range optical fiber communication. That is, information is committed over a very long range, that is around thousands of kilometers, and for that we don't need much of loss. So we need gain in the system, and for that what do? We need optical amplification. And for optical amplification, we what do we require? We require stimulated emission. So is that there is optical amplification without much loss, with less of loss or more of gain, what we say. So these erbium doped fiber amplifiers are capable of amplifying light in 1500 nanometers, which will minimize the loss, and we will get the signal as we had, we get the signal it won't be a weak signal. It would be very much like the signal which is transmitted at the transmitting end. So the core of the fiber is doped with erbium. Now here erbium is a very rare element, and it provides laser amplification by stimulated emission. So now we talk about that this is stimulated emission. So what do we say? So this is stimulated emission. That means we need to pump the atoms in the ground state to one of the excited states. And so for pumping, what are we using? We are using a laser diode. So here we have a laser diode, and this laser diode is actually used for pumping. Okay, so this laser diode, what it will do? It will pump the atoms, erbium atoms in the ground state to one of the excited state. And if this will be pumped in the excited state, and since erbium has a longer lifetime, so the population, population inversion, more of atoms in the excited state than in the ground state. That is what we call as population inversion. This population inversion will be maintained for a longer time. What kind of time? Till the time a signal photon arrives. Okay, as soon as a signal photon arrives, it will stimulate the atoms in the excited state to drop down, and in the process it will emit a clone photon as that of the signal photon. Okay, so this erbium silica fibers behaves as a 3-level laser at room temperature, which is at 300 Kelvin. So what do we have here? Here we have erbium atoms in the ground state, and we will pump it using this laser diode, and in the process this is done at a wavelength of this is lambda pump, and this will be done at a wavelength of 980 nanometers, and it gets excited to the second excited state. Now from here there will be the excitation to the first excited state, and that will result in heat radiation. Now I have my signal photon. Okay, this is signal. Okay, sorry, I'm sorry. So this is my lambda signal, and this signal photon gets de-excited, comes down to what? 1500, comes down to the ground state, and there will be emission of the 1550 nanometers. So this is my this is how light is amplified using by doping the erbium atoms in a silica fiber. Okay, so this is very helpful. These are erbium doped fiber amplifiers, and they are used in optical communication systems, that is to transmit signals over very long distances. Okay, it transmits signals over thousands and thousands of kilometers. So with that, we move on to the very first question of our session, that is the EDFA. Erbium doped fiber amplifiers are generally operated in the wavelength range near, which we have done in our previous slide. What is the wavelength range in which this fiber amplifier is operated? This is 1550 nanometers. Okay, this is the wavelength range in which my fiber is operated. Now let us move on to the next signal. So as I said, next question I want to say, this is the wavelength of the signal. Okay, now let us move on to the next question. So 1550 nanometers gets amplified. Okay, signal in this wavelength range gets amplified. So which wavelength is most appropriate one for pumping an EDFA? What do we rate? That this is a 3-level system: excited state 2, excited state 1. Okay, this is the ground state. There is pumping. Pumping is done using a laser diode. So what is the wavelength range of that? That is 980 nanometers. This is pumping wavelength. Okay, so what do we learn? That lambda pumping is equal to 980 nanometers, and lambda signal is equal to 1550 nanometers. Okay, so let us move on to the next question. The optical gain in an erbium doped fiber amplifier depends on the following factors. So as I had told you, that why are we using or doping the fiber amplifier, a fiber optic with erbium atoms? We are making it a fiber amplifier. This fiber amplifier will amplify the signals which is traveling through, which has been transmitted from one end to the another end over thousands and thousands of kilometers. That is, if we have a black box, it's very much like a transistor. We have some signal over here, say S, and this is my amplifier over here. It will amplify a signal to NS, and here this N is known as the gain of the system. So this gain for an erbium doped fiber amplifier, what should be it dependent on? How to understand what is that is, gain is output by input over here. So what it should be dependent on? First of all, for amplification, what do we need? Population inversion. So when will the population inversion be more? When there is a lot of doping concentration. So more the doping concentration, more will be the gain. That is, gain will be dependent on the doping concentration. Then again, the pump power. Pump power, that is, the pump is used to pump the atoms in the ground state. That will be absorbed. The pump will be absorbed by the atoms in the ground state, and it goes to the excited state. So more the pump power, more will be the what shall I say? Gain, and the length of the dope fiber. So the pump power depends on the length of the fiber. So if the pump power is P0 over here and pump power is PL over here, so the gain in the power, that is PL by P0. I am sorry for my mistake. PL by P0. Got it? Okay. So this will be equal to, how much this should be equal to? This should be equal to exponential of integral, that is into atoms in the excited state into the emission cross section minus the atoms in the ground state into the absorption cross section, and this integration is done over the whole length of the fiber, 0 to L. So this length is L. Integration is done over the whole length of the fiber. Integration, quite untidy. Okay, so this integration is done over the whole length of the fiber. So this is my fiber, this is P of 0, and this is P of L, and this is the whole length of the fiber. Okay, so this is my gain. So the gain is equal to exponential of what? Into sigma into ES minus N1 sigma AS into, this will be dz, okay, into L. Okay, so it is dependent on the length of the dope fiber. So the answer is all of this. Which of the following pump wavelengths are used in the EDFA? I have already talked about that EDFA is a 3-level system. This. These two are the excited levels, E2 and E1. This is the ground state level. We have already talked about one of the pump signals, that is 980 nanometers, and this is the next pump signal, which is 1480 nanometers. Okay, so these two will be the answer. 1.48 micrometers and 0.98 micrometers. So the pumping is done using these two wavelengths. Okay, why? Because there is significant absorption cross section for erbium doped silica at 980 and 1480 nanometers. Moving on to our next question. So till now we have discussed about what are the factors the gain of EDFA dependent on: doping concentration, the length of the fiber, the pump power. The pumping wavelength is 980 nanometers. It can be 1480 nanometers as well, but there is a catch over here which we'll learn in our next question. And the signal which the EDFA amplifies is 1550 nanometers. Next, which pumping scheme is advantageous in terms of noise figure when we use 1480 nanometers radiation as a pump in EDFA? One is co-directional, other is counter-directional, then both or none of them. Which pumping scheme should be advantageous? First of all, you need to understand between the difference of co-directional and counter-directional. This is my fiber. This is my pump. This is my pump, and this is my signal that we want to amplify. So this is what you call counter directional. Okay, then there is another I'm so sorry, please excuse me for my sloppy diagrams. This is again a fiber. Here we have lambda pump and we have the signal. So this is co-directional. Okay, so This is a 1400 nanometers pumping. How much is lambda signal for EDFA? 1550 nanometers. So should both of them be given in one direction? Of course not. Yes. No. It should be counter-directional. Why it should be counter-directional? Because since both pump, which is 1480 nanometers, and the signal photon, which is 1550 nanometers, these wavelengths are very close to each other. So it will be very hard to filter out the pump from the signal. Okay, so what we have to do, we have to use a counter-directional pumping so that we can avoid this problem. Okay, we can it will be easier to separate out the two signals or the filter out the pump from the signal if both are counter directional. Okay, if the pumping is at a wavelength of 1480 nanometers for an EDFA. Okay, it should be co-directional in this case. Okay, next. Here we have two statements. One is assertion. Assertion is just a statement. It can be correct, it can be a false statement, and there is another statement which is the reason. So reason and assertion can both be correct, or assertion and reason can both be false, or we can have both assertion, reasoning correct, but reason might not be the correct reason for assertion, and then again or the reason can be a correct explanation for assertion. So over here we have bidirectional pumping, that is pumping from both the directions of the fiber. What do you mean by bidirectional pumping? Pumping from both the directionals of the fiber. Okay, so this is my fiber, this is pumping from here, this is pumping from here. So this bidirectional pumping, what happens? Why are we doing bidirectional pumping at both the ends? That is there can be some reabsorption, that is reabsorption because of some absorbing centers, some scattering, all these things can be done. So pumping from both ends, what can help in this? Okay, it can help in the gain. If there is less of absorption, there will be less of loss. So if there is less of loss, there will be more of gain. So bidirectional pumping will provide more net gain. So the answer should be A. Both A and R are correct, but R is the correct explanation for A. Okay, now let's move on to our next question. Now this question is a very interesting question. Okay, and it is a bit involved too. So over here, what do we have? Let's see. We have an amplification of light which is at a wavelength of 1800 nanometers, and this is another material, not EDFA. This is thulium doped silica fiber. It has some doping concentration. So as we talked about doping concentration, it is per meter cube. So this is my Na, the number of atoms at which this fiber is doped, and this is my lambda signal. Okay, the signal photon which we want to amplify. Amplification of light at a wavelength of this. Okay, now we need to assume that there is uniform excitation and pump signal overlap factor of 0.93. Okay, we'll come to this. What is pump signal overlap? So let's say this pump signal overlap is lambda. Okay, so we have this fiber. There we have the pumping signal, and this is a signal. So both of them are at the same time. The pump and signal should be what? Synchronized. Okay, there is no pumping and we have a signal, so there will be less of gain. Why? Because there will be less of amplification, that is no pumping, and we already have a signal. The signal and pump are not synchronized. Then what will happen? More of the atoms will be in the excited state, and will be in the ground state. So there will be less of population inversion. Less of population inversion, less of amplification means less of gain. So the pump and the signal should have some overlap, great amount of overlap. If there is pump and after a very long time we have the signal, that is, there is no overlap time between them. That means again the atoms, they can be spontaneous emission, no matter because the excited state has some certain lifetime, and my signal comes after the lifetime of the after the time after a time when the atoms in the excited state drops down, then there is population inversion. So there's less of population inversion, less of amplification, so less of gain, so more of loss. So now what do we have over here? See there, so there should be maximum pump signal overlap, and this range is between 0 to 1. Okay, and over here what do we have? We have 0.93, the overlap factor. It's a 0.93 overlap. Now this TM silica fiber, this is the pump signal overlap, and around approximately 85% of the ions are in the excited state. 85% of ions are in the excited state. So it is talking about the fraction of the ions. This is not N2. Okay, so certain fraction of the ions are in the excited state. So this is some fraction of the ions in the excited state. Say small n2. Okay, are in the excited state, and my length of the fiber is 1. 1, that means this is L. Okay, that is the length of the fiber. We have to assume that the transition and the transition cross-section includes both emission as well as absorption cross-section. Transition cross-section graph is shown as below. So we have to find the value of the small signal gain, that too in dBs. So we should convert this log factor. We'll have some exponential, we'll convert the exponential into log, and then we'll have to convert that log factor into dBs, which we have learned how to do. So from this graph, what information does this graph tell us? It tells us about the cross section. That is a transition cross section, which includes the absorption. This is absorption cross section, that is the red is sigma A, and let's say I'll write CS, and this blue is emission. Okay, emission cross section. Okay, so this blue is emission cross section, the red is absorption. This is sigma E and this is sigma A. So assuming so we have to find the emission and the absorption cross section at the signal. So here we have 1800 nanometers of the signal. So this would be my sigma E, which is more than 3. Is that so? Yeah, it is more than 3.5. Wait, yeah, that's the case. And at 1800 nanometers, this is my absorption cross section, which is less than 1.5 but greater than 1, so 1.3. Okay, because it's between 1 to 1.5. Well, let's say 1.3. So we see that over here the absorption cross section is less than the emission cross section. Always try to find as much as data you want. Absorption cross section is less than the emission cross section. That means we'll have a sufficient gain in this. Okay, so now how do we do this problem? How do we solve this problem? Let's move on to solving this problem. Okay. Okay, so we have all the relevant information which is required to calculate the small signal gain in terms of dBs. So this gain is equal to, what is it equal to? It is equal to exponential of what? The length of the fiber, the pump signal overlap, which is lambda, times the number of atoms in the excited state, which is N2, times the absorption emission cross section. Okay, that is already found from the graph, which is the emission cross section, minus the number of atoms in the ground state times the absorption cross section. All right, so here what information we don't have? We have the emission cross section, absorption cross section, the pump signal overlap, that is the lambda, and the length of the fiber. We don't know N2 and N1, that is the exact number of atoms in the excited state. But instead of that, we have been given some information. What information are we given? We have been given information about the, I'm sorry, this is the wrong color, I've picked, so this color, right. We have been given information about the total number of atoms that is used for doping, the concentration of the atoms. And also what information we have been given? We have been given fraction of ions in excited state. Okay, so let's say that is N2. This N2, small n2, is equivalent to capital N2 by Na. That is the concentration of the ions in the ground state. So N2 by Na. So we have been given that N2 is 85%. So this capital N2 can be written in terms of the fraction of the ions in the excited state times Na. What is Na over here? The total number of ions. Okay, so we sorted out with the number of atoms in the excited state. Now, how many number of atoms are there in the ground state? So we know that out of the total concentration, that is out of 100%, 85% is in the excited state. So how much percent will be in the ground state? Right, definitely it will be around 15%. Okay, so my number of atoms in the ground state, as I said, 15%. So this N2 will be equal to, actually this N2 is 85%, that is equivalent to 0.85. So number of atoms in the ground state will be 1 minus 0.85, which is 0.15. So this is equivalent to 1 minus N2, that is small n2, times Na. Okay. So now what are we supposed to do? We just plug in this capital N2 and capital N1 into this gain expression and find the gain. Okay. So G is equal to exponential of the length of the fiber times the pump signal overlap, that is pump signal overlap time, times what? We like to write the number of atoms in the excited state in terms of the concentration and the fraction of ions in the excited state. So this will be N2 times Na minus 1 minus N2 times Na. Alright? Yeah, this is completely alright. Okay, I am missing out one factor, that is the cross section, transition cross section, that is sigma ES and sigma AS. Yeah, it's completely alright now. Okay, those sigma ES and sigma AS is found from the graph, that graph of cross section with the wavelength, transition cross section with the wavelength, and at a wavelength of 1800 we found that sigma ES is equal to 3.7 E minus 25 and sigma AS is 1.25 E minus 25. So now this gain expression will be how much? Let's just simplify this expression a bit. That is, we need to do some what of the maths. So in this math, what are we supposed to do? Let's see. Okay. Okay. So this will be N2 times Na times N2 sigma ES. Let's do one thing. Na, yeah. Let's take N2 also common. Okay. N2 times sigma ES minus, should it be minus or plus, into sigma ES? Okay, it should be plus, into sigma ES minus what? Na sigma ES. Sigma ES. Is it all right? Yes. So now this is an exponential. Let's convert it into log. And when you convert into log, you'll get some 10 log base 10. And when you calculate that, you'll get a factor. What factor is that? That factor is 4.343. Just convert the exponential to log and the log into dBs. Just multiply it and you'll get G is equal to 4.343. Okay. Length of the fiber, the pump signal overlap times what? Times NA times N2 times sigma ES plus sigma AS minus sigma AFS. Okay? Is this all right? Yes, I suppose completely all right. So now you have all the relevant information. You need to find the small signal gain in terms of the you have a correct expression to find the small signal gain in terms of dB, in terms of the relevant information that has been given in the question. Okay, so just do the calculations, verify it with this calculation, and if you find any discrepancy, please let me know about it so that I can correct it over here. Please, I would urge you not to depend on this calculation, but do your own calculations. Again, if there is any discrepancy with your calculations, just let me know so that I can also recheck it and correct it out. Okay? So now, moving on to our very next question. Let's see what our next question is about. All right, so we have done a very heavy problem out there. Now, let's see how many of you have watched the laboratory experimental demonstrations which are available to you in this week. So this week laboratory experimentation was done on EDFA, these optical fibers. So in this laboratory experiment, we have talked about counter-directional and co-directional pumping. So which pumping configuration is used and why? I would urge you to look into the laboratory experimental demonstrations videos which has been shared with you. And in that, to achieve low noise figure, we need low noise figure. Low noise figure means what is noise figure? Noise figure is a ratio of the signal to noise, right? Signal to noise ratio at the output to signal to noise ratio at the input. And that should be as minimum as possible. So to achieve low noise figure, we are doing counter-directional pumping. Okay, counter-directional pumping to achieve low noise figure. Again, in the laboratory experimental video, what type of photodetector is used in the light runner kit? So we have different types of photodetectors, like silicon photodetector, indium gallium arsenide photodetector, gallium arsenide photodetector, germanium photodetector. So all these photodetectors, okay, all these photodetectors work in certain wavelength range. So I would urge you, I would request you to find out the wavelength ranges in which these if used as a photodetector will be operated. So in the laboratory demonstration experiment, indium gallium arsenide photodetector was used. So what I want you to do is find the wavelength range of all the materials used here. You got it? Good. Very good. It's good. Find the wavelength range and do let me know about all the wavelength ranges in the next class. I'll ask you about it. Okay? Okay. So now, as I said, the answer is indium gallium arsenide, and I want you to tell me the reason for that. Why are they using indium gallium arsenide? Okay, so our next topic. Our next topic is light amplification for stimulated emission. Okay, so lasers mean, as I have already said, light amplification for stimulated emission. So this laser light, okay, I haven't written it, but all of you know about what is the full form of laser. We are doing amplification by stimulated emission. So why stimulated emission? Because this stimulated emission, they have spatial and temporal coherence. That means they remain coherent. Coherent means that is they are having a definite phase difference for a longer time, that is temporal coherence, and for a greater length. Okay, for whatever length there is coherence, and for a longer time, long time and long length, that is long spatial coherence. For a longer distance, their light is remaining or the light, the photons are maintaining a constant phase difference. Now this laser light is highly directional. What do you mean by highly directional? Why this laser? So what is the meaning of highly directional? So okay, let me give you a very simple example. Say you have a torchlight. Where do I draw this? Okay, say you have a torch. This is my torch source. Sorry. Say you have a torch. TURCH. Okay, this is my torch source. If I emit light from here, so it spreads over a wide range. The spatial spread, that is from like this, it goes this way. It separates out, right? So the spread is quite a lot. That is, this theta is lot for the torchlight, for any light, for the light from our mobile phones, right? If I give this light from my mobile phone, so you see how much it is spreading out. Okay, it spreads out a lot. But in case of a laser, it's highly directional. That is, for a longer length, for much longer length, it's just one line. It's just line like this. Okay, one line. That spreading from here is quite less. Okay, for a longer distance, it will be for like this, for a longer distance, and even if there's a spread, the spread will be quite small. Okay, that's why we are calling it, it's highly directional. Now, narrow spectral width emission. What is the meaning of narrow spectral width emission? That means if we look at the intensity of this laser light, if we look at a graph, let's say we draw a graph of the intensity of this laser light with the wavelength, and this intensity is in arbitrary units. Say this intensity is in arbitrary units. So it will be very intense. Laser lights are very intense, and it's very narrow, quite narrow as a function of wavelength. So this full width half maxima. So by now I think you must know what is the meaning of full width half maxima. So this full width half maxima is quite small for a laser light. That is, it means it is highly monochromatic. Okay, it means it is highly monochromatic. So these are the properties of the laser light. Now let us move on to building a laser. So what do we need? What are the important components that are required when you need to build a laser? What are the important components? So one of the important components, you need a medium. Medium in the sense, some material having these energy levels in them, in between the energy levels of which your lasing is taking place. So this is amplifier for the light wave. This acts as an amplifier. This active medium will act as an amplifier for my light wave. All right. Okay. So this active medium will contain the atoms, molecules, ions, or say for example the ruby. Ruby is chromium dipsapphire, ruby, the helium neon gas for a gas laser, or the carbon gas as the active medium. Okay, so it contains atoms, molecules, or ions like erbium, ruby, helium neon, which are excited using a what? Using a pumping source. Anything can be a pumping source. Okay, so here we pump this active medium. It can be bidirectional pumping. Okay, it can be signal direction depending on the gain and the losses of the active medium and how you design the laser. So this is the manner in which we provide the pump. So this pumping is done to achieve what? Why do we pump our active medium? We are pumping an active medium to achieve population inversion. Achieve population inversion, right? Okay, so pumping is done to achieve population inversion. Okay, and this can be done electrically, this can be done optically, or this can be done by collisions. So where do we get this pumping by collisions? Helium neon gas. Okay, there is collision of the atoms and electric discharge will be passed. There will be collision of the first kind, and some other materials there are collisions, mechanical collisions of the second kind, and we get pumping. That is, the atoms of the ground state gets excited to the excited state. So after this pumping source, now we need amplification. Okay, we are getting amplified. But when we need more and more amplification, what we'll do, we'll make this light which we get oscillate. Okay, this will oscillate forward, backward. So an oscillator is required. Okay, in this oscillator. So to get oscillations, we will introduce some feedback. Okay, so that the part of the output energy will be utilized. It will be fed back into the system so that there will be more and more amplification. So this resonator will is used to get oscillation. These oscillations will introduce feedback. Okay, it will introduce feedback in our system. Now, I would say that we have already worked about one of the optical oscillators in our previous lectures. Can you answer? What is that oscillator? I'll give you one hint. The hint is that it is an interferometer. It's an optical oscillator. So any hint? Any guesses to what kind of oscillator was used? It's an interferometer. Yes, it's a Fibre interferometer. So in a Fibre interferometer, we have these two light sources, and our light is oscillating forward, backward, so that it will provide amplification. So Fibre oscillator is one of the optical isolators, and it can be used as an optical component or as an optical resonator to amplify our systems. Okay, so now let us move on to our next part. On the next question. The next question is the Boltzmann ratio. The Boltzmann ratio, or the relative population of two energy states at room temperature is T is equal to 300 Kelvin, which is given as 1 by E. Now we have to determine the wavelength of the emitted radiation due to transition between these two states. Okay, one hint is already given to us. It's a Boltzmann ratio. So we know which principle to be applied in solving this problem. The Boltzmann statistics. Okay, so we have these energy levels E2. We have this energy level E1. It has some population N2. It has another population N1. So we know that atoms gets excited, go here, it will get excited and it will emit some radiation. We have been asked to determine the wavelength of that radiation. That is delta E is equal to E2 minus of E1. So what is the Boltzmann formula that we'll be using over here? We'll be using N2 by N1. What is N2 by N1? It is equivalent to N2 by N1 is equivalent to E2 by N1 is equivalent to exponential of minus of E2 minus E1 minus E2 by E1 by kBt. Some brackets have been misplaced here and there. Sorry about that. Minus exponential of E2 minus E1 divided by kBt. Now I have already told that E2 minus E1 is equal to delta E. And this delta E would be the energy of the emitted radiation. So this emitted radiation has an energy of delta E. Okay. This will be the energy of the emitted radiation. So this is equivalent to exponential of minus of delta E by kBt. Okay. Minus of exponential of delta E by kBt. Now we have been given that at room temperature, that is T is equal to 300 Kelvin. We know how much is kB. So at room temperature, this N2 by N1 is 1 by E. That is N2 by N1 is equal to 1 by E. That is E to the power minus 1. So I can just rewrite this 1 by E as E to the power minus 1. Now what do I have to do? We just equate the exponents. That is 1 is equal to delta E by kBt. That is implying that delta E, delta E is equal to kBt. Okay. Now we have been asked to find the wavelength of this emitted radiation. So now we can find how much energy is this, but we can relate the wavelength to energy. And what is the formula for that? That is what is the formula for that? Hc by lambda is equal to kBt. So from there you can find out lambda. Alright. I think that is more than enough. We know h, we know c, we know lambda, and we know t. Okay. Just find out how much is lambda. Okay. Okay, so this is a very easy question. I'm not going to solve all of it. I will give to you as a homework, and I'll ask you in the next class for this. But I'll definitely going to give some hints regarding how to solve this question. So the question is about an optical resonator, and this resonator is in air, which is n is equal to 1, and we know the length of the cavity. That is, if we have this resonator. We have this resonator. This is n is equal to 1 and the whole length is 10 centimeters. Okay, this length is 10 centimeters and we need to determine the number of modes which is present in the wavelength range of 4 nanometers above the central wavelength. So this is an optical resonator. So light will be traveling like this, right? It is fed back. Okay, forward, backward, backward, forward. So what do we get in this? What are we getting? We are getting standing waves. Okay, we are not getting traveling waves, but we are getting standing waves. And since we are getting standing waves, that these number of waves are known as modes over here. Okay, how many modes are gonna survive in this? So for this we have one formula, which is these modes will be m into what? C by 2nl. N is equal to 1. Okay. Now m is equal to what? M is equal to 1, 2, 3. It will tell us about the number of modes present. So this mu m over here means that only certain frequencies, sustain over here. sustain in the cavity. Okay, so if you want to find the separation between these nodes, that is the separation, frequency separation between the nodes, what will you get? I'm sorry. So delta nu will be equal to C by 2NL. This is the separation between the nodes. Okay, so this is the separation between the nodes. That is, we have one node over here, there is another node over here. So there is this frequency separation. So what are we given over here? We are given lambda. So now we know delta nu. We are given about delta lambda. So I hope you'll be able to solve the question, right? So I think enough. Yeah. So yeah, where were we? Can you hear me?
Yes.
Yeah. So where were we? We were into this. Now I hope you can solve this problem. I've given you all the hints. I'll tell you the answer. The number of modes is number of required modes. The number of required modes is 3200. So from here you can proceed, I guess. Okay, you have all the relative information. You know delta lambda, you know lambda, you know L. So there's just one catch over here, which is a very simple catch. I hope you can find it out and just let me know how you solved it. Okay, so let's move on to the next problem. Next problem is a very simple problem. Just the use of formulas. Nothing else to be done in this problem. Okay, I am given the line center, the wavelength, that is the signal wavelength. Okay, I have been given the absorption coefficient also. Okay, the absorption coefficient in thermal equilibrium, it's given at room temperature, is equal to the gain coefficient. Okay, that will be the negative of the gain coefficient. And I have also been given about how many atoms are there inside, and I'm given about the length of the gain medium and the refractive index as well, and also the cross-sectional area, and operates on this transition. So what are the information that I'm given? I'm given the radiation, absorption coefficient, the atoms that have been doped. I'm given about the length of the medium. I've been given about the doping constant. Both its ends are polished. What else am I given? Both its ends are polished and coated so that each has a reflectivity, that is R1 and R2 is also I'm given, that is 80%. I'm given a transition line width, that is delta nu. Okay, and also I'm given something else, 1.8. This will be small n, not bigger n. This will be n is equal to 1.8. Okay, my question is, determine the transition cross section that given a spontaneous lifetime. What is the transition cross section? There's a formula to that, which is related to the transition cross section is at certain frequency proportional to the inversely proportional to TSP, directly proportional to lambda, and to the gain. And this this is line shape transition, and this line shape transition is inversely proportional to the width in the transition width. Okay, and I hope you remember all these things. What is line shape transition? What is the transition width? Last time I told you everything. Transition, this G of nu is coming, because these energy bands, they are not just a discrete band, they are very closely spaced lines, and there is a spread in it, and because of this there is a spread in the frequency, and therefore we have this transition line with delta nu. Okay, that's how the line shape width is coming. So we
Can you
have all
switch
these.
to the question, please?
Yeah, sure. This question?
No, the main question.
Yeah.
The transition cross section is given here, 2 centimeter square.
That's a cross sectional area, not the transition cross section.
Yes.
That is different.
Okay.
We have to find out absorption or the emission transition cross section. This is the cross sectional area, across which area, but across which area the transition is taking place.
Yes.
Okay, we are given that this laser makes use of 15 centimeter long gain medium of cross sectional area. The gain medium will have some cross sectional area. Across what cross sectional area the gain medium is spread, because we have this resonator in this, the gain medium is here. So this gain medium will have some cross section area, but that doesn't mean that will be the transition or that is the absorption of the emission cross section area. We have to find that out. Okay. So this is it. So this is how we find the absorption cross section area. So let's move on to the next question. Assuming that there is no extraneous loss, determine the resonator loss coefficient. That is, we have to find alpha R. So which formula are we going to use? Alpha R. Alpha R is equal to alpha int into plus 1 by 2L ln of 1 by R1 into R2. We are given R1, we are given R2, and we have been told that we have to assume that there is no loss, extraneous loss. Okay, that means this alpha int, which is loss, that is equal to 0. Okay, alpha int is the loss coefficient. Okay, this loss coefficient is 0. Okay, so if alpha int is 0, then alpha R is equal to 1 by 2L ln of 1 by R1 into R2. Okay, so this I would ask you to check the calculations. Okay, just check the calculations and let me know what the answers are. Okay. The next question. Assuming there is no extraneous losses, determine the resonator photon lifetime. How will you determine this T photon? That is the average lifetime. How are you going to define it?
Average lifetime is equal to 1 by C into resonator loss.
Yes. Not 1 by actually. It will be N by C into the resonator loss. That is alpha R. Because it is a lifetime, right? So this lifetime will be depending on the speed. And when we talk about speed, we'll have to get the refractive index in which the light is traveling. Okay. So that is equal to N by C alpha R. So just substitute the values. We know N, we know C, how much is the speed, and we know alpha R. We have calculated it. Okay. So this will be the answer. So next question is about the finding the threshold population. That is NTH. That is, threshold population means the minimum amount of population inversion. And we have been told that this laser is pumped and gamma of mu0 increases from initial thermal equilibrium value. That means instead of negative, it is now a positive. It has changed sign. That is, there is a gain. So that means there is a minimum population inversion, and that is what we have to find. Okay, and that population inversion, as we know already, that is given by alpha R by the absorption coefficient, and We know the absorption coefficient we have already calculated. The cross section, the transition coefficient, and we have already calculated this, and alpha r also we have already calculated. So we have to find out. So I want to ask you, for lasing to happen, for effective lasing to happen, what should be this threshold gain? Should it be the maximum or minimum? What should be this threshold? There is a certain minimum amount of population inversion is required. Okay. So N threshold for lasing to happen, we need some minimum amount of, at least some minimum amount of minimum inversion. Okay, and when are we going to get that minimum inversion? Threshold means from where the lasing will start, stimulated emission will start. That means threshold over here. And when are we going to for threshold inversion? When are we? What are the requirements? That is requirements for minimum population inversion. What are the requirements for minimum population inversion? From all these things, what did you learn? That is number one. We talked about the photon lifetime. Okay, this T photon should be as long as possible. Okay, this is one thing. Second thing is that TSP, that is the spontaneous time. Should this be long or should this be short? This is a spontaneous lifetime.
Long. Short.
Right. This should be as short as possible. Okay. Why this should be short?
It will increase noise.
So the thing is, TSP is small. That will increase my sigma. Okay. Sigma over here is the transition cross section. Right. That sigma will increase. And if my sigma increases, then my N threshold will decrease. That is, at a very small population inversion, we can start off lasing. Okay. I think you're getting this point. You're getting these relations and logical things, right? And then the third thing is this G of nu, which is inversely proportional to delta nu. This line width, should it be small or short, long? Should be as small as possible. Okay, and also it depends on the laser material. The fourth thing is laser material. These are the requirements for minimum population inversion. Okay, why it depends on the laser material? So that N threshold can be kept as small as possible, so that we don't require a large pumping power. If N threshold is really small, then we don't require a large pumping power. Okay, so with this I end my class. Thank you class, thank you so much. I hope you guys got the gist of the lasers and also about EDFA. If there are any doubts, please revert back to me, and please write in the discussion forum, or you can mail back to me. Okay, thank you so much. We'll meet next week the same time. Thank you so much. We'll meet the next week the same time, and next week we'll talk about the lasers. Thank you Thomas, thank you Sajdev. Goodbye, have a good day ahead and a good week ahead.